Hey everyone, this is Muhammad Nadeem and welcome to my YouTube channel. Today in this video, we will explore the concept of the Gauss law. That what is the Gauss law, what are its implementation, what are the main points for this Gauss law. So first we will start this video from the statement of the Gauss law. Then we will go for the derivation of expression for this law, and then we will focus on these important points in the form of question. So the first point is, what is the flux when the surface encloses the charge? So in Gauss law, we always consider a Gaussian surface. So this question means that if the charge Q present inside that Gaussian surface, then what will be the implementation of the Gauss law? The second point in the form of question is, why does not the size of the surface matter? Because the Gauss law claim that the size of the surface does not matter. So in this video we will go for a reason behind that. The third question is, why does not the shape matter in finding the flux? So the shape of the Gaussian surface around the charges does not matter. If we take up a cone-like shape, a sphere-like shape, a cylinder-like shape around a charge, it does not matter according to a Gauss law. And the fourth point in the form of question is, what is the flux when the charge is not inside the surface? So if we consider a Gaussian surface and the charge do not present inside that Gaussian surface, so in this case what will be the Gauss law? And the next point is, what are positive flux through that enclosed Gaussian surface? What is the negative flux and what is the zero flux through that Gaussian surface? And the last point is is the flux through a closed surface is always zero? So all these points we will discuss in this video in more detail. So let's start the video. As you know this model, as I am following this in our videos, so here this is a positive charge and around it there are large number of electric field lines. This is the positive charge. In this case, this electric field lines is radially moving outward from this positive charge. So let's consider Gaussian surface around that positive charge. This is actually the 3D form, the 3D ball-like shape around that positive surface. So this is actually a sphere around that positive, around this positive surface. So the electric field lines are radially outward from this sphere-like shape. Here I am going to consider a small surface from this ball, from this sphere around the positive charge. This is a small surface. So as we know that a surface having magnitude, the surface having area, and the magnitude of the area is length multiplied width. So area is equal to length multiplied width. Okay, and the direction of the area in this case is perpendicular to this area. So here the direction will be this is the direction of the area. Okay, in this case, if you see here the electric field lines which is come inside from the positive charge, which is present inside this ball, the electric field line from that positive charge will come towards you. Okay, mean that perpendicular to this area. Okay, let's consider this same area here, then it will be easy to understand for you. This is actually a area I am considering here. So the in this case the direction of the area is perpendicular to this area. In this case, the direction of the area is in this direction. Okay, from the left to right. and the charge which is enclosed inside this sphere will have some electric field lines, and that is moving radially away from that positive charge, and hence in this point the direction of electric field lines, which is always in this also in this direction. Okay, in this case flux is equal to E electric field lines. We know the definition of electric flux is this: the number of electric field lines, that pass through the area. Here del a small area I consider on the sphere around the positive charge. So this is the flux through that small area. So in order to replace this dot, we will put the cos theta here. So the flux through that small area is equal to E, and instead of this dot E, and this is del A, and instead of that dot I will put the cos theta, because this is the dot product here. And phi in this case is equal to E del A cos of theta. Okay, and this theta is actually the angle between the electric field lines and the direction of the area. Here the electric field lines, here the direction of the area is in this, from left to right, and the direction of electric field lines from the positive charges present here at the center of this sphere is always also from the left to right. So the angle between these two lines is 0, because they are parallel to each other. So let's put here the angle theta is 0. So phi is equal to E del A cos of 0. And we know that cos 0 is equal to 1. So phi is equal to E del A. And now consider the same differential area here. So the electric, in this case the direction of the area is perpendicular to this area. So in this case the direction of the area is this, and in this case the electric field lines, the direction of electric field lines is moving away from this positive charge. Okay, and this direction is also parallel to the direction of the area. So the angle between the area and the direction of electric field line here is also 0, because they are parallel to each other. In this case this was here the flux through this area was phi 1. In this case the flux through this small area is phi 2. So for phi 2 the electric flux equation is, this is actually phi 1. Okay, now phi 2 is equal to E del A cos of theta. In this case the electric direction of this area and the electric field line is also parallel to each other. In this case the theta is 0, and hence E del A cos of 0, and we know that cos of 0 is equal to 1, and it becomes E del A. Okay, and similarly I consider this area. The direction of this area will be perpendicular to this area, and the electric field line is also here moving perpendicular to this area, and therefore the angle between the direction of the area and the electric field line is the same, and therefore the angle between that is 0, and in that case the phi 3 is also written here. So phi 3 is equal to E del A cos of theta. In this case the theta is also 0. So for this cos 0 we can write 1, so it become E dot del A. So phi 3 is also become E dot del A, and in this way we will write this for all these small areas, and also become here in this area, and in this area, and in this area. So in this way I will take the flux for all these differential area of this Gaussian surface. So up to n, so here I'm going to write that for up to phi n. Okay, for these large number for each for this specific area. So for phi n, the expression will be E del A cos of 0, because in this case the electric field line and the direction of the area will be also in the same direction, and therefore the angle between them is 0, and this also become E del A. Okay, so this is the flux through that Gaussian surface. So we will proceed this further. Now I am going to calculate the total flux. So the total flux V total is equal to phi 1 plus phi 2 plus phi 3 up to plus phi n. So phi total in this case is equal to phi 1. The value of phi 1 is taken from here, which is equal to E del A plus here the value of phi 2 is E del A, and plus the value of phi 3 is also E del A, and plus up to phi n. The value of phi n is also E del A. Okay, so for the summation of all these values, we use in mathematics a sign which is called a summation sign. So for here I am going to put that sign, which is this. So phi total is equal to summation sign of E del A. It means that we have to add large number of E del A from this equation. So here focus on this. This sphere is actually at the same distance from the positive charge. Okay, this sphere is actually from the same distance from the positive charge. So therefore the number of electric field lines through each point here at the same distance from the positive charge is the same. Therefore we can say that in this case the electric field intensity is same on this surface. Okay, so here in this equation we will put this electric field intensity out of this summation sign. So phi total is equal to E summation of del A. Here this is the summation of del A, mean that we have to add all these del A. So here if I add all these differential area, it will give us the area of the sphere. So in this case the summation of del A is actually the area of the sphere. So phi total is equal to E and the area of the sphere, Okay, this is actually the area of the sphere, and we know that the area of the sphere is 4 pi r square. So put that here. Now pi total is equal to E, and the area of the sphere is 4 pi r square. Okay, here we also know this is actually electric field intensity, and the equation for electric field intensity is this: E is equal to 1 over 4 pi epsilon naught Q by R square. This is the equation for the electric field intensity. So put the equation, this equation instead of this E. Then that equation become equation become phi total is equal to, now here put the value of E instead of this E. So the value of E is 1 divided by 4 pi epsilon naught Q by R square. Okay, and then we will multiply that with 4 pi R square. So 4 pi R square. So here cut this R square with this R square, this phi with this phi, and this 4 with this 4. Okay, here the remaining thing in this equation is in above there is a Q. Okay, Q is present here. Okay, Q is remaining here, and in denominator this 4 has cancelled, this phi and this R also cancelled, but only epsilon not remain here. Okay, and this is the Gauss law. The Gauss law is actually state that Gauss law state that the total flux through this closed area, the flux through this closed area or this closed surface around this charge, this positive charge. So the flux through that closed area is equal to the charge enclosed inside this surface. In this case, this is only one positive charge. So the total flux through a closed area is equal to the charge enclosed by that surface divided by the permittivity of free space. In Gauss law, we derive the expression for the flux through a closed surface, which is equal to the charge enclosed by that surface divided by permittivity of free space. Here, this is more important. Only we will focus on the charge which is enclosed by this surface. So let's this is the first case. In case A, we have the flux through this surface is equal to the flux through this A case surface is equal to the charge enclosed by this surface, which is equal to 2 microcoulomb divided by the permittivity of free space. The value for the permittivity of free space is 8.85 multiplied 10 raised to the power minus 12 coulomb square per Newton per meter square. Okay, and in this way we will find the Gauss law for the flux through this closed surface. And now for the case B. Here in this case, similarly, this is same case, because here the phi through this closed surface is equal to the charge enclosed by this surface, which is minus 2 microcoulomb divided by the permittivity of free space, which is 8.85 multiplied 10 raised to the power minus 12 coulomb square per Newton and per meter square. Now in third case, we have charges. One is this charge, other one is this charge, and the other is this charge. So here in case C, in this case the flux through a closed surface according to the Gauss law is equal to the charge enclosed by this surface. In this case, only this plus 2 microcoulomb charge is enclosed by this surface, this Gaussian surface. This plus 4 and this minus 2 is out of this Gaussian surface. Therefore, the Gauss law for this case is only the charge enclosed by this surface, which is plus 2 microcoulomb, okay, and divided by the permittivity of free space, which is 8.85 multiplied 10 raised to the power minus 12 coulomb square per Newton per meter square. Okay, and now this is the case D. In case D, the flux according to the Gauss law is equal to the charge enclosed by the surface. In this case, the charge enclosed is minus 4 microcoulomb, minus 1 microcoulomb, plus 6 microcoulomb, and divided by the permittivity of free space, which is 8.85 multiplied 10 raised to the power minus 12 coulomb square per meter, and coulomb square per newton, and per meter square. Here we will not include these charges, which is plus 4 minus 5 here. Okay, because according to the Gauss law, only the charge enclosed by this surface will be we write here. Okay, in case E, the charge enclosed by in this case, according to the Gauss law, the flux through a closed surface is equal to the charge enclosed by this surface, which is 4 microcoulomb minus 10 microcoulomb plus 6 microcoulomb. Okay, we will not write these two charges. One is plus 3 microcoulomb and other one is plus 2 microcoulomb. Okay, because this is out of this Gaussian surface, and all of them divided by 8.85 multiplied 10 raised to the power minus 12 coulomb square per newton per meter square. So this is the concept of the Gauss law, that we will put only the charges which is enclosed by the surface, and we will not include their charges which is out of the surface. According to the expression of the Gauss law, which is phi through a closed surface, the flux through a closed surface is equal to the charge enclosed by that Gaussian surface divided by the permittivity of free space. So according to this expression, the Gauss law does not depend upon the shape, upon the size of the Gaussian surface. According to this law, the flux through this surface will be equal to the flux through this surface. So the mathematics behind this claim is that. So before going to that, I'm going to discuss this figure a little bit. So this is actually that positive charge which is present at the center, and this is a small sphere around that center positive charge, and the distance from the center to this sphere is r. Okay, in this small sphere, the distance in other words, we can say that the radius is equal to r. And now this is the large sphere, and now in the same way I consider the large sphere at the distance 2r from the positive center, positive charge at the center. So here this Gaussian surface is actually r distance away from this positive charge, and this is actually the capital R distance away from this positive charge, and this capital R is equal to 2 times of the small r, the radius of the large sphere. The large sphere radius is equal to, which is actually r, is equal to 2 times of the small r. In first case, we consider the small sphere. So the Gauss law for this sphere is small sphere is written as phi through a closed surface is actually flux is actually the number of electric field lines that pass through the area. Okay, in this case the summation of del A is actually the area of the sphere, and which is equal to 4 pi r square, and the value of E, the electric field intensity, is equal to 1 over 4 pi epsilon naught q by r square. This is the value of electric field intensity, and that is multiplied by 4 pi r square. So multiplied by 4 pi r square. So here cancel this r square with this r square, pi with this pi, and this 4 with this 4, and the result become phi is equal to q divided by epsilon naught. This is the first case. Okay, now we are going towards the second case. The second case is for this large sphere. So this is for this large sphere around the positive charge which is present at the center. So the flux through that large sphere is equal to the electric field lines that pass through the surface multiplied by the area. Okay, the electric field line that pass through the area. Here we have summation of del A. In this case, the summation of del A is the area of the sphere. So the area of the sphere is 4 pi. In this case, this is capital R square. 4 pi capital R square. Okay. Now the expression for the electric field line is this: phi is equal to 1 over 4 pi epsilon naught q by this capital R square. Okay, and then multiply that with 4 pi this capital R square. Now cancel these things, this R square with this R square, pi with this phi, and this 4 with this 4, and the result become pi is equal to q by epsilon naught. So here we conclude that the result from this first case for the small sphere, which is this, is equal to the result for this large sphere. So these two are equal. These two expressions are equal. Therefore, we can say that the Gauss law does not depend upon the size of sphere, the size of the Gaussian surface. According to the Gauss law, the flux through a closed surface do not depend upon the shape of the Gaussian surface. So according to the Gauss law, the flux through this shape, which is a circular, will be equal to the flux through this shape, which is an irregular shape. According to the equation of the Gauss law, which is according to expression of the Gauss law, which is the flux through a closed surface is equal to the charge enclosed by this surface divided by permittivity of free space. So here is no parameter for this irregular shape. So this Gauss law expression is independent of the shape of the Gaussian surface. Here let's consider this charge is a positive charge. Okay, there will be electric field lines originating from this positive charge and radially outward from this positive charge, which are these lines. So these are the lines which are these are electric field lines around this positive charge. So the number of electric field lines that pass through this shape is actually equal to the number of electric field lines that pass through this shape. Here let's consider we have 1, 2. Okay, we have here 1, 2, 3, 4, 5, 6, 7, 8. 8 lines are passing through this spherical surface around the positive charge, and similarly we have irregular shape around this positive charge. So the number of electric field lines passing through this irregular shape are 1, 2, 3, 4, 5, 6, 7, 8. So the number of electric field lines that pass through this spherical shape is equal to the number of electric field lines that pass through this irregular shape. So according to the Gauss law, the flux through a closed surface do not depend upon the shape of so the according to this Gauss law, according to the Gauss law, the flux through a closed surface, the flux through a closed surface do not depend upon the shape of that closed surface. Okay, in other words, we can say this closed surface called a Gaussian surface. And now we will answer the question that what is the flux when the charge is not inside the Gaussian surface? What is the flux? What is the flux when charge is not inside the Gaussian surface? Okay, then what will be the flux when the charge is not inside the Gaussian surface? So according to the expression of the Gauss law, which is the the flux through a closed surface is equal to the charge enclosed by that surface divided by the permittivity of free space. So here the charge enclosed, this is actually a Gaussian surface, okay, and this is the charge plus q which is present outside of this Gaussian surface. So the charge enclosed by this Gaussian surface in this case is 0, because there is no charge enclosed by this Gaussian surface. So here I am going to put so the charge enclosed is equal to, sorry, the flux through a closed surface is equal to the charge enclosed. The charge enclosed in this case is 0, so 0 by epsilon naught is equal to 0. In this case, the flux according to the Gauss law is 0. So why? What is the mathematics behind this to explain this? So so here we have a positive charge and the electric field lines moving away from it in this direction. Okay, and this is other electric field line moving away from this, and this is the area when it entering into the Gaussian surface. When this electric field line entering to the Gaussian surface, it passed through this area, and similarly this electric field line is moving away, is coming out from this Gaussian surface with the area dA2 and enter with the area of dA1. So the flux here when this line entering is actually given by this, is actually given by this. So in this case the flux is equal to E dA1, in this case E dA1 cos of theta. So here in this case the direction of electric field line is in this direction. Okay, the electric field line originate from this positive and moving in this direction, and the direction of this area is in this direction. So the theta between these two direction is actually 180. So put 180 here instead of theta. E is equal to E dA1 cos 180, and cos 180 is equal to minus 1. In this case it becomes E minus E dA1. Similarly, the flux through this area when the electric field line is coming out from this Gaussian surface. So here the flux through this area is given by this is actually a flux through 1, and this is flux through this area 2 is actually equal to the electric field lines E dA2, electric field line passing through the area, and cos of theta. In this case theta this is the area, okay, and the direction of the area, is this is the direction of the area, and the direction of electric field line coming from the positive charge is also in this direction. Okay, the angle between these two is here, it is 0, so put 0 in this equation instead of this, theta, so E dA2 cos of 0. So here cos of 0 is equal to 1, so it is equal to phi 2 is equal to E dA2. This is actually phi 2. Okay, now the total flux through a closed surface. Now the total flux is equal to phi 1 plus phi 2. The value of phi 1 is phi total is equal to the value. Now the value of phi 1 is here is the value of phi 1. This is the value of phi 1, which is minus E dA1, and the plus the value of phi 2, which is plus E dA2, okay. Here this area A1 is equal to this area, both area are same, so dA1 is equal to dA2. Okay, here this become minus E dA1 plus E. Here instead of this dA2 I put dA1 because dA1 is equal to dA2, so here this is become dA1. So this is minus dA1 and this is plus dA1, and this is equal to 0. So therefore the Gauss law says that the flux through a closed surface will be 0 when there is no charge present inside that Gaussian surface. At the last, we are going to differentiate between positive flux, neutral flux, and negative flux. Neutral flux is actually when the number of electric field lines entering the Gaussian surface is equal to the number of electric field lines leaving the Gaussian surface. In this case, the number of electric, if we put positive charge outside of the Gaussian surface, the number of electric field lines entering this Gaussian surface is equal to the number of electric field lines leaving. So the number of electric field lines entering is 1, 2, 3, 4, 5, 6, 7. Okay, and leaving the number of electric field lines leaving this Gaussian surface is 1, 2, 3, 4, 5, 6, 7. So the number of electric field lines entering this Gaussian surface is equal to a number of electric field lines leaving this Gaussian surface. Therefore, we call this a neutral flux, because there is no charge inside this Gaussian surface to increase or decrease the number of electric field lines entering to the Gaussian surface. In this case, this is actually a dipole. The flux through a dipole is also a neutral, because inside a dipole, in dipole we have negative charge and the positive charge, and this negative and positive charge are enclosed by the Gaussian surface. So the effect of the negative charge is cancelled by the effect of the positive charge, and therefore no electric field lines leaving this Gaussian surface. So if we put the positive charge here, the number of electric field lines which entering to this Gaussian surface and leaving this Gaussian surface will be equal, because in this electric field line there will be no influence of the dipole present inside, because the charges present inside have cancelled the effect of each other. Now the positive flux is defined as if the number of electric field lines entering is equal to, if the number of electric field line entering is less than the number of electric field line leaving Gaussian surface. Okay, in this case, if I consider a Gaussian surface, this is a Gaussian surface, and the number of electric field lines entering is, let's say, they are 4 in number. Okay, and the number of electric field line leaving is 6 in number. 1 2 3 4 5 and 6. In this case, we call this a positive flux. So what is happened inside this Gaussian surface to increase this electric field line? So if we put a positive charge inside this Gaussian surface, the number of electric field lines, the electric field lines also originating from this positive charge. So that line also meet with the external electric field lines entering, and therefore the overall number of electric field lines leaving this Gaussian surface will be more. So now the negative electric flux is actually defined as the number of electric field lines entering is greater than is greater than the number of electric field lines leaving the Gaussian surface. In this case, if I consider a Gaussian surface, this is a Gaussian surface, and the number of electric field lines entering 1 2 3 4 is greater than the number of electric field lines leaving this Gaussian surface. This is because inside this Gaussian surface there will be some charge present. So in this case, that charge is negative, and this negative charge, the electric field line of this negative charge are entering radially inward towards itself. So when the external electric field lines entering to this Gaussian surface, that electric field line also have chances to enter into the negative charge. So some of them will be enter to this negative charge, and some of them will moving outside from this Gaussian surface, and therefore we say that the number of electric field lines entering is equal to a number of is greater than the number of electric field lines leaving.